Bohr's theory established the concept of atomic energy levels, but did not thoroughly explain the wave-like behavior of an electron. Current ideas about atomic structure depend on the principles of quantum mechanics, a theory that applies to subatomic particles such as electrons. Light exhibits wave-like behavior, as well as particle-like behavior. The term wave-particle duality is used to describe this dual nature of light. Wave-particle duality of light. The wave and particle pictures of light should be regarded as complementary views of the same physical entity. The equation E is equal to Planck's constant time frequency displays this duality. E is the energy of the particle, of the photon, and the frequency, is the frequency of the associated wave. The first clue in the development of wave-particle duality came with the discovery of the Boggle A relationship. In 1823, Louis de Broglie reasoned that if light exhibits particle aspects, perhaps particles of matter show characteristics of waves. He postulated that a particle with mass m and a velocity of v has an associated wavelength. The momentum is the product of the mass times the speed. The equation lambda is equal to Planck's constant divided by mass and velocity is called the Boggle A's wavelength. It is now generally accepted that wave characteristics apply to all matters. However, for large masses, the Boggle A wavelength is too small to detect. A consequence of the wave-particle duality is the uncertainty principle. In 1927, Heisenberg showed from quantum mechanics that it is impossible to know both the position and the velocity simultaneously, which is referred to as Heisenberg's uncertainty principle. Electrons are moving, therefore if we try to locate it by bouncing a photon off it, the electron's location would be affected as well. Wave-particle duality and the uncertainty principle resolve the problem regarding the stability of the nuclear atom. Classical mechanics predict that the electron would crash into the nucleus, indicating that the nuclear structure is not stable. Therefore, classical mechanics could not explain experimental results involving the nuclear structure. We could no longer think of an electron as having a precise orbit, meaning spherical around an atom. To describe such an orbit would require knowing its exact position and velocity. It became evident that classical mechanics is just an approximation on a macroscopic level. A more general theory was needed in order to account for observations on a microscopic level, which led to the birth of quantum mechanics. Quantum mechanics is a branch of physics that mathematically describes the wave properties of submicroscopic particles. This is a probabilistic theory as opposed to a deterministic one. In quantum mechanics, we do not try to locate particles. We only try to calculate probabilities or likelihoods of finding particles in whatever region we are interested in. Schrödinger defined this probability in a mathematical expression called a wave function. An orbit is a wave function that gives us information about an electron, a description of the region around the nucleus where we're most likely to find an electron. For each atom, ion, or molecule, quantum theory gives us an infinite set of orbitals that we can use to describe the electrons. It is convenient to refer to these orbitals by a set of numbers called quantum numbers that is unique for each orbital. According to quantum mechanics, each orbital describing electrons has 4 quantum numbers. First, there's the principal quantum number n. This can only be a positive integer. N is equal to 1, 2, 3, etc. Orbital angular momentum quantum number L can only be a positive integer that is less than n. And L is typically equal to 0, 1, dot, 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 to n minus 1 for any particular quantum number set of n. Magnetic quantum number, m sub L or m, can only be an integer from minus L to plus L. So that would be minus L dot 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 to 0 dot 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 to plus L. Spin quantum number, m sub S, can only be minus a half or plus a half. Orbitals can be classified into shells or levels, which gets us to the principal quantum number n, which represents the shell number or energy level in which an electron resides. The smaller the n, the smaller the orbital. Smaller the n is, the lower the energy of the electron. It may be an integer from 1 to infinity, although greater than 7 as far as today are unimportant. N determines the size and energy of the orbital, the affected volume of space the electron is moving about. Orbitals can also be classified into subshells or sublevels. This just gets us to the second quantum number, orbital angular momentum quantum number L. This distinguishes subshells within a given shell that have different shapes, the shape of region or volume that the electron occupies. Each main shell n is subdivided into subshells. Within each shell of quantum number n, there are L subshells, each with a distinctive shape. L can have any integer ranging from 0 to n minus 1. The different subshells are denoted by letters. So, if L is equal to 0, we refer to that as an s orbital. L is equal to 1, we refer to it as a p orbital. L is equal to 2, d. L is equal to 3, f. L is equal to 4, g, and so on and so forth. In general, the number of orbitals that belong to the same subshell is equal to 2L plus 1. So, if we're talking about L is equal to 0, talking about an S, 2 times 0 plus 1 equals 1. There is only one orbital in an S subshell. L is equal to 1, talking about a P. 2 times 1 plus 1 equals 3. There are 3 orbitals in a P subshell. L is equal to 2. D. 2 times 2 plus 1 equals 5. There are 5 orbitals in a D subshell. L is equal to 3. F. 2 times 3 plus 1 equals 7. There are 7 orbitals in an F subshell. We can say that S orbitals come in a set of 1, P orbitals come in a set of 3, D orbitals come in sets of 5, F orbitals come in sets of 7, etc. Each orbital in a subshell has a unique m sub L quantum number, which we'll be covering next. The magnetic quantum number m sub L, or sometimes referred to as just m, distinguishes orbitals within a given subshell that have different shapes and magnetic orientations in space. It is the magnetism caused by the orbital motion of the electron around the nucleus that affects the orientation. Each subshell, S, P, D, F, is subdivided into orbitals, each capable of holding a pair of electrons. There is a maximum of 2 electrons per orbital orientation. M sub L can have an integer value from minus L to 0 to plus L. Each orbital within a given subshell has the same energy. All NLs have the same energy for all orientations, but not each L, meaning 4S is a lower energy than a 4P, and 4P is at a lower energy than a 4D, and 4D is a lower energy than a 4F. So when we say 3D orbital, we mean any one of the 5 orbitals in the 3D subshell, meaning minus L to 0 to plus L, in this case D being 2, minus 2, minus 1, 0, plus 1, or plus 2. We're saying that all these 5 orientations are all at the same energy. See, all 5 of these all have the same energy. So, we know L is equal to 2. We know that we have M sub L, which is minus 2 to 0 to plus 2, meaning that we have minus 2, minus 1, 0, plus 1, and plus 2. These 5 orbitals are available in the 3D orbital subshell. We also know that each one of these has a maximum of 2 electrons in each one of these, which means there's a maximum of 10 electrons in the 3D subshell. Here's a picture of the spherical shape of an s orbital. Notice that n equal 2 is larger than n equal 1 because it's getting into a larger size as we go up in levels of n. L equals 0 are referred to as S subshells and are spherical in shape. There is only one magnetic orientation, M sub L 0, for the S subshell. Here's a look at the 2p orbitals. L equal 1 are referred to as P subshells, and they are dumbbell in shape, going in 3 different orientations. One along the x-axis, one along the y, and one along the z-axis. There are 3 magnetic orientations. We refer to them sub L as minus 1, 0, and plus 1 for the different orientations, your x, y, and z, for the P subshell. So therefore, there's a maximum of 2 electrons per orientation. So therefore, the P subshell, there's a maximum of 6 electrons possible. Here's the representation for the 3D orbitals. L equal 2 are referred to as D subshells and are cloverleaf in shape. There are 5 magnetic orientations, M sub L representing by negative 2, negative 1, 0, plus 1, plus 2. Remember, M sub L is minus L dot 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 to 0 dot 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 to plus 0. So L equal 2 would mean we go from minus 2 to plus 2. In this particular thing, we could see there's also a maximum of 2 electrons per orientation. Which means for D level, there is a maximum of 10 electrons, 2 per orientation. In general, the nth shell has n squared orbitals. For n equal 1, n squared equal 1, 1 squared, there is only one orbital. So we're talking about 1 in the 1s. Quantum numbers n is equal to 1, L is equal to 0, M sub L equal to 0. And there's only 2 electrons available in the 1s orbital. For n squared, n equal 2, n squared equal 4. There are 4 orbitals. You have 1 in the 2s, quantum numbers n equal 2, L equals 0, and M sub L equals 0, which there is 2 electrons. Then you have 3 orbitals in the 2p. That's n equal 2, L equal 1, 1 being for p. And M sub L, you have minus 1, 0, and plus 1. So therefore, if you can have 2 in each orientation of M sub L, then you have 6 electrons. So there's a total of 8 electrons in your n equal 2 level. For n equal 3, n squared equal 9, 3 squared equal 9, there are 9 orbitals. You have 1 in the 3s, n equal 3, L equals 0 for s, m sub L equals 0. So you have 2 electrons. There's 3 in the 3p's. You got n equal 3, L equal 1 for the p, m sub L, 3 orientations, minus 1, 0, and plus 1. Therefore, we have 6 electrons. And 5 in the 3d's. You have n equal 3, L equal 2 for D, m sub L, minus L to 0 to plus L, meaning minus 2, minus 1, 0, plus 1, plus 2, which means 10 electrons. There's a total then of 18 electrons in n equal 3 level. For n equal 4, 4 squared equals 16. There are 16 orbitals. You got 1 in the 4s, n equal 4, L equals 0 for s, m sub L equals 0, that's 2 electrons. 3 in the 4p's, n equal 4, L equal 1 for p, m sub L, minus L to 0 to plus L, minus 1, 0 plus 1, that's 6. Remember, 2 in each orientation. 5 in 4d, n equal 4, L equal 2 for d, m sub L, minus 2, minus 1, 0 plus 1 plus 2, which is 10. And 7 in the 4f, n equal 4, L equal 3, 3 for f, m sub L, minus L to 0 to plus L would be minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3. That's a total of 14. Add those up, that would be a total of 32 electrons in n equal 4. Here's a table putting together all the information that we just discussed. First column is your energy level, N, quantum number N. Second column is the shape, which is your quantum number L. We can determine L by 0 to n minus 1. So you can see for n equal 1, we can only have 0 available, which is referred to as an S. For n equal 2, we have 0 to 2 minus 1 is 1, so we have 0 and 1 available, which would be S and P. For n equal 3, 0 to 3 minus 1 is 2. That means we have 3 levels, 0, 1, and 2, meaning S, P, and D available. For n equal 4, we can go 0 to 4 minus 1, which would be 0 to 3, which is 0, 1, 2, 3, which means we have S, P, D, and F available. The third column is the orientations, your M sub L. That means you go from minus L dot 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 to 0 to plus L. So first one, n equal 1, all we have is 0 available. For our n equal 2, we have 0 for the S. And for the P, we can end up having minus 1, 0, and plus 1. That's similar to that orientation slide where we said PX, PY, PZ, showing the different orientations. For the third level, you have 0 for the S. You have minus 1, 0, and plus 1 for the P. And then you have minus 2, minus 1, 0, plus 1, and plus 2 for the D's. That's similar to that orientation slide we show the different D levels. Then 4, you have an S. You have the 3 P's, minus 1, 0, plus 1. D, minus 2, minus 1, 0, plus 1, plus 2. And then we have the S, which is minus 3 all the way to plus 3. How do we note these subshell notations? 1S, the 1, the numbers being the N, and the second being the letter for the shape of L. So we have 1S, 2S, 2P, 3S, 3P, etc. The fourth column tells me the number of orbitals in the subshell. That's just talking about here. We've got 1, 1. I have 1, 2, 3 of my subshells of my P's. My D's, I have 5. And my F's, I have 7. And then the maximum electrons. Remember, there's only can have 2 electrons per orientation. So 2 in the S's, 6 in the P's, 10 in the D's, and 14 in the F's. The magnetic properties of atoms suggest that electrons have an intrinsic magnetism due to their spinning motion in addition to the magnetism that is generated by their motion around the nucleus. The motion of an electron around a nucleus, m sub L, can be compared to that of the planet revolving around the sun, while electron spin can be compared to that of the rotation of the planet around its own axis, which we would call m sub S. The spin quantum number m sub S refers to the two possible spin orientations, spin up, which would give us a plus 1/2 term, and spin down, which is a minus 1/2, of the electrons residing within a given orbital. Remember, they can only have 2 electrons in any particular orientation. Each orbital can hold only 2 electrons whose spins must be opposite in one another. So in that orientation, those 2 electrons will say one is plus 1/2 and one is minus 1/2. Thus, an electron in an atom is completely described by specifying 4 quantum numbers, n, L, m sub L, and m sub S. The quantum numbers n and L tell us the shell and subshell. The quantum numbers m sub L tells us which orbital, and m sub S tells us which spin. No 2 electrons can have the same 4 quantum numbers. If 2 electrons have the same n, L, and m sub L, meaning the same orbital, they must have opposite spin and different m sub S's. Pauli exclusion principle. No 2 electrons may have the same set of 4 quantum numbers. Where 2 electrons occupy the same orbital, they must have opposite spins, m sub S plus 1/2, m sub S minus 1/2. The maximum electrons that we can assign to an orbital is 2, meaning one with spin up plus 1/2 and the other with spin down minus 1/2. Let's do some questions now to see if we understand the stuff that we just covered. How many electrons can be assigned to a 4p orbital? The key to this question is that we're talking about a orbital, one particular orbital. So the key to the question is they're referring to a single 4p orbital. For any single orbital, the limit is 2 electrons. One electron would spin up with ms equal plus 1/2, and one with a spin down. ms is equal to a negative 1/2. How many electrons can be assigned to 4p orbitals, meaning 4p subshells? Orbitals meaning plural. All the 4p orbitals. How many electrons can be given to that? Key to this question is that we're referring to all the 4p orbitals or subshells. The 4p orbitals come in a set of 3. Remember, L is equal to 1 for p. So that means I got minus L dot 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 to 0 to plus L. So that means I have a minus 1, a 0, and a 1 for my orientations for my 4p's. There's a maximum of 2 electrons in each orbital. That means I have a total of 6 electrons that will have n equal 4 and L equal to 1. Each one of these will have 2 electrons. They will differ in m sub L and m sub S values. The 6 possible m sub L, m sub S values will be as follows. You would have 3 orbitals would spin up 1/2, meaning your negative 1, your 0, and your positive 1. And then you will have 3 of them would spin down, meaning your negative 1, your 0, and your 1, giving us a total of 6 possible sets of quantum numbers there. How many electrons can be assigned to the n equal 3 shell? That means all subshells, S, P, D, whatever available. In the n equal 3 shell, there are 3 subshells. There's a 3s, a 3p, and the 3d. The 3s subshell consists of 1 orbital with 2 electrons. The 3p subshell consists of 3 orbitals with 2 electrons in each given 6 electrons. That would be your negative 1, your 0, and your positive 1. The 3d subshell consists of 5 orbitals with 2 electrons in each, making it 10, minus 2, minus 1, 0, plus 1, plus 2. So the total number of electrons that can be assigned in the n equal 3 shell is 2 plus 6 plus 10, which is 18. In general, since there are n squared orbitals in the nth shell, the number of electrons that can be assigned to a shell is 2n squared. So an easy way to get to that answer of 18 would be to follow the 2n square. 2n squared at n equal to 3, your third shell, that would be 3 squared is 9, 9 times 2 is 18, which gets us to the answer of 18. Which of the following can accommodate the most number of electrons? A 4f orbital. Well, in this case, we're talking about a single orbital. A single 4f orbital will accommodate a maximum of 2 electrons. Now, next one, we're talking about the 3D subshell. So we're talking about the whole thing. So we're talking about -2, -1, 0, +1, and +2. It has 5 orbitals, which is at -2, -1, 0, +1, +2, which means 2 in each one of those, which is a total of 10. Next, we're talking about the n equal 2 shell. So we're talking about all the different types of shells that are available in n equal 2. Well, you know that goes to L is equal to 0 to n minus 1, which means all we have there available is 0 and 1, your S and your P. So we will have our S, which has 2, and then your P would be your -1, 0, +1 again. So you're going to have a total of 8. So n equal 2 has 4 orbitals, L equals 0, which is your S. And you have 1 of those. And then your L equal 1, which is P, and you have 3 of those. That's a total of 8. Last one is, once again, a single 3D orbital. So the maximum orbital can have is 2, so that answer is 2. So the answer is the 3D subshell will have the most, with a total of 8, with a total of 10 electrons in it. Homework 60.